So this is the way we've always written complex numbers. That's the format. A plus bi. Where A is the real part, B is the imaginary part. That's an example. In that particular case, the real part is 2, and the imaginary part is 3. So what I want to look at is how can you graph that? Right? We've never graphed complex numbers, but graphing 2 plus 3i is exactly like graphing the point 2 comma 3. That's exactly what it's going to look like. So to graph complex numbers, we're going to use 2 axes, but we're not going to think of them as an x and a y. We're going to think of the 2 axes as the real and the imaginary, r and I. That's how we're going to think of it. So graphing on a plane, when you don't use x and y, but you call them r for the real and I for the imaginary, that's called the complex plane. It's just like graphing on x and y. You're just calling the 2 axes different names. Right, so this is not trig form yet. This is still using what we call standard form. It's the one we've been using all along. You'll know when it's trig form. When we have trig form, you're going to start to see trig in it. You're going to see like sines and cosines. Okay, there's no sines and cosines in 2 plus 3i. Okay, so that's a picture of the complex plane. The real axis takes the place of the horizontal x, and the imaginary axis takes the place of the y. So to graph something like 2 plus 3i, the real part is 2, the imaginary part is 3. That means go 2 to the right and 3 up. And that's how you graph 2 plus 3i. We'll try a few more of those. Any questions on that?
I'm just looking weird. Where does the Bermuda Triangle fall in the imaginary field?
Where does the Bermuda Triangle fall?
I think it's pretty imaginary.
Yeah, I would think it might be imaginary. Bless you. Okay, so here's some complex numbers, and let's see if we can graph them. Okay, so remember, the horizontal, that is the real axis. Vertical is imaginary. You can't switch them. If you switch them, it's like switching x and y. It's not right. Okay, what's the real part in -4 minus 2i? And what's the imaginary part? -2. Just -2. So -4 needs to go which way? Left 4, and the -2? Down 2. So 1, 2, 3, 4, 1, 2. So that's that one. Okay, let's try this one. -2 plus 3i. Starting at the origin, which way am I going to go to graph that? Left 2.
And up 3.
Up 3. Yep. So left 2, up 3. How about 5 up?
Up 5.
That's just up 5. It has no real part. You could think of it as like 0 plus 5i. Just up 5. And how about 6?
6 right.
You're going to go 6 to the right. And what about the imaginary part?
0.
Yeah, it's 0. It doesn't have it. Yeah. So that's that one. Hey, Any questions on graphing those? All right, let's look at the red one. The red one has a certain distance you could measure from here to there. What do we call the point where the two axes cross? That's the origin. Now, in one dimension, we have a name for something where you measure the distance from where the number line starts. A number line doesn't have a name. Well, I guess you can call it the origin. We usually just call it 0. So if you look at how far something is from 0, there's a name for that. Well, it's the same name we're going to use here. What do you think you call the distance from this point to the origin?
Value.
What is it?
Value.
What kind of value?
Absolute.
Absolute value, yes. So in 2D, the concept of absolute value is just like 1D.
But 3D.
3D, you still have an origin. So it's like the distance from wherever you are to where the x, y, and z axes all cross. Now, what shape do you think I could make to figure out the length of that black line?
Triangle.
Yeah, you can make a triangle out of it.
You're a right triangle.
Yeah, make a right triangle. And how long is the bottom side?
2 units.
2 units. Well, that was the real. And how tall was it?
3 degrees.
3. That was the imaginary. So all you have to do is take the real part, square it. Take the imaginary part, which is 3, square it. And in Pythagorean theorem, what do you do with those two things?
Square root of sum.
Yeah, take the square root of the sum. So that's going to be the square root of 13. And that's really the hypotenuse in that triangle. But that's called the absolute value. It's the distance from your point to the origin. Yeah?
At what level of calculus do you start graphing in 3 dimensions?
You graph in 3D even before that. I would say you could start graphing stuff in 3D in pre-calculus. Yeah, it's not as common because it's hard to do 3D on paper. So if you're going to graph 3D, you probably want to use some kind of computer software to do it. But when you're solving systems of equations, if you had 3 variables like x, y, and z, that would be a good candidate for graphing in 3D. If you wanted an application of 3D graphing that was at the pre-calculus level. There are applications of 3D graphing in calculus too, but I'm just saying there are applications even before that. Not so much in Algebra 1, really, because unless you solve systems with 3 variables in Algebra 1, usually, I guess it depends on your teacher, but that's more like Algebra 2. Okay, so here's the notation. 2 vertical bars means they want to know the absolute value. And it's really just the Pythagorean theorem. So here's your complex number. Real part is A. Imaginary part's B. Plug them into the Pythagorean theorem. And you'll find the hypotenuse of your triangle, which is the absolute value. Let's try an example. So this time, the complex number I'm going to work with is 3 plus 4i. So if you want to visualize it, you can. Okay? Where is 3 plus 4i? Yeah. And how do you get there?
Go 3 to the right and 4 up.
3 to the right and 4 up. So what I want to find is that. So make a triangle. 3, and that's 4. Okay, so follow the formula. the square root of, what's a in my case? 3. And what's b? 4. And 3 squared is 9, 4 squared is 16. So that's the square root of how much? 25, which is 5. So that's the absolute value of 3 plus 4i. Okay. Since it measures a distance, what kind of number do you think it always has to be? Yeah, it always has to be positive. Okay. Question on that? All right, now let's look at this point again. I'm just going to move these away. But I want to add something in. Okay, so I want to think of that point now as being on the edge of a circle. It's on the edge of a circle. What would this
Radius.
be now? Right, it's the radius. And we just found the radius of that circle. It's exactly what we just did over there. How much did it come out to? 5. When you are writing a complex number in trig form, one thing you have to know is how big of a circle the point is on. And in this case, the size of the circle is a 5. So that's one thing you need to know. The other thing we need to know is from here, how much did you rotate to get up to there? That's the other thing you need to know. Now, if I put this side back in, right here. The amount that you rotate in red is really this angle right there in that triangle. So if we can figure out how big this angle is and how long that radius is, those are the two things we have to figure out to write that number the new way. Now, you're going to know this side, and you're going to know this side. If you were standing right here, what position is this side over here? Opposite. And what position is this side right here? Adjacent. So what trig function has those two? Tangent. That's how you figure out your angle. It's going to involve using tangent. Okay, so the radius is Pythagorean theorem, and the angle uses tangent. Okay, so let's write that down. So in trig form, you are not allowed to have an x, and you're not allowed to have a y. X and y is what we call standard form. Nothing wrong with it, it's just x and y is standard form. It's not trig form. So we have to get rid of these two things in trig form. All right, so let's take same kind of picture I had before, except this time I don't know the sides are 3 and 4. Okay? I know the sides are x and y. And r I don't know. It's just r. I don't know what it is. Okay. Here's the angle that we talked about in the lower left. Okay, let's start with finding the cosine of that angle. What's the formula for cosine?
Opposite over hypotenuse.
That's sine. Opposite over hypotenuse.
Cosine?
Cosine.
Adjacent over hypotenuse.
Adjacent over hypotenuse. Okay. What side is adjacent in that picture?
X.
X. And what side is the hypotenuse? R. So now, if you got x by itself, well, how would you do that? How would you get x by itself and put the r on the other side?
R.
Yeah, you'd multiply it. So now we have a formula for the x. We're going to be able to get rid of the x. And we're going to replace it with r cosine theta. Okay. Now we're going to do the same thing for the y. What's the definition of sine?
Opposite over hypotenuse.
Opposite over hypotenuse.
Y over R.
Opposite is y. Hypotenuse is r. And we'll do the same thing. If you get y by itself, by moving the r to the left, what would be in that box?
R times sine.
R times what?
Sine is Y.
Sine of theta. Now you have a formula for y. If you substitute in those two things that I'm pointing to right there, that will change your complex number to trig form. Let's write that down. So instead of x, you're going to fill in r cosine theta. The I just stays right where it is. Nothing happens to that. And instead of y, you fill in r sine theta. Any question on how I got the r cosine theta or the r sine theta? It just comes from looking at that right triangle.
So, R is just like the hypotenuse, is that what it is?
R is the hypotenuse.
Okay.
Yeah.
Okay.
Yep. Now, what do this term and this term both have in common?
R.
Yeah, they both have an R. When two things have the same thing in common, it's like the R has been distributed out to it. What's it called when you reverse distributing? What's the opposite of the distributive? Factoring. So we're going to take that R, and instead of having it be distributed out, we're going to factor it out. And that is how you write a complex number in trig form. So let me show you an example of a final answer, okay, for a complex number in trig form. Okay. Let's say I had this. I'm keeping the two numbers the same because the angle is easy for me to do in my head if I do that. In trig form, it would be square root of 8 cosine. Anyone think they know? We haven't really talked about it yet. I mean, I kind of gave you a hint that you're going to use tangent to figure out this angle. But if you go over and up the same amount, what kind of angle is that? Yeah.
45.
It's a 45. That's an example of what a final answer looks like in trig form. We'll talk more about it. How did I get this and how did I get this? We'll talk about that right now. But that's a final answer. You don't do anything with that. If you took this square root of 8 and you distributed it out, started to do it all out, you would be changing this back to standard form. Yeah. I guess if you want to check your answer, you could do that. But in general, once you get it this way, we just leave it. That's a final answer right there.
Wait, why did we put the I?
Why do we put the I? Because that was been there since the original problem.
No, like, why is it flipped?
Why did it flip? Oh, instead of yi.
Yeah.
It's just how they normally write it. I mean, there's nothing wrong if you put the I at the end, because that is normally where we put it. But in this format, for some reason, they put it before.
Okay.
But it's the same thing if you put r cosine theta plus sine theta I. One guess I have why they don't put the I at the end is because if you write this, what I'm confused about is this I part of the argument or not part of it?
Oh, okay.
Okay.
So it's the same reason why they don't put the.
It's like with a square root. if you had to do square root of 3 times 2, that looks confusing to me. Do you mean square root of 6? Or do you mean that? So if you put it before it, then there's no question it's not part of the square root. Same with the I. If you put it before it, there's no question it's not part of the argument to sign.
That makes sense.
Yeah, so that's why they do it. Okay, so to use that format, there's 2 letters you need to be able to figure out. R, which we just talked about. This is R. Oops, I don't want to erase it. How do you figure out R when you know the other 2 sides? Yep, Pythagorean theorem. And the other thing we need to figure out is theta. Theta is the angle with the x-axis. That's this angle right here. And what trig function did I kind of give you a hint earlier that you're going to need for that? Tangent. Yep, something with tangent. So we're gonna write that down on the next page. Yeah.
Can you scroll up a little bit? I have a question about something you wrote. Right there, where it says, so like the thus x plus I y. Are you saying that turns into that, or that they're the same thing?
So I'm saying that if you take this, if you take this and that and fill them in here and here, you get what's underlined in red.
Okay.
So you're substituting in for x and you're substituting in for the y, the 2 formulas in those boxes.
Okay.
The side angle side formula would work for that, right?
So,
Find.
no. Yeah. We're gonna always use the r cosine theta plus I sine theta. Yeah. Okay, so how do you find the r and the theta? Well, kind of already written this down. To find r, you use the Pythagorean theorem. It's the radius of the circle, but it's really the hypotenuse of the triangle. So that's how you find r. Now, if you use theta on that triangle, you would have tangent theta equals, and what would go on the other side? What is tangent? It's opposite over adjacent. What's the opposite in that triangle? Y. And what's the adjacent? X. Now, the goal isn't to find tangent theta. The goal is to find theta. So tangent needs to disappear. How are we going to get rid of tangent?
Arctangent.
Yeah, we're going to use the arctangent or the inverse tangent. So if you're trying to find an angle in quadrants 1 or 4, the formula is the inverse tangent of y over x. Well, how do you know if you're in quadrants 1 or 4? Well, that's why I taught you earlier how to take a complex number and graph it. So you graph your complex number, and then you know if you're in quadrant 1, 2, 3, or 4. That's how you know. So in quadrants 1 and 4, we can do the inverse tangent of y over x. If you're in quadrants 2 or 3, because those are on the other half of the circle, you need to add 1/8. So it's almost the same formula. You do the same thing. But if your point is in quadrant 2 or 3, to get this angle right here, do the inverse tangent, but then add 1/8. If you were working in radians, you'd be adding pi. Okay, so that covers how to find the radius. Use Pythagorean theorem. It covers how to find the angle if you're in quadrant 1, 2, 3, or 4. Where else could you be besides quadrant 1, 2, 3, or 4?
On the actual axis.
You could be on an axis. Now, if you're on an axis, think of like this point right here. What's the x value of this point?
0.
0. I don't know the y value. There's some y value. But the x value is 0. What would happen if you tried to plug in 0?
On the point.
Yeah, you'd run into a problem. These formulas don't work if you try to plug in 0 for x, because you'd be dividing by 0. So if you end up with a point on an axis, here, 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 or here, you have to memorize that the answer is either 0. What about if you're straight up? What angle is that?
90.
90. And this one?
180.
And then this one?
270.
270. Yep. So if the point is on an axis, it's either 0, 90, 180, or 270. So I wrote them in radians and degrees. Okay. And that covers everything that we need to know about how to write a complex number in trig form. How you find out the radius from the origin, and how you find the angle using inverse tangent. So now we'll try changing a few numbers that are in standard form, like this one, into something like this one. And then this is the hardest thing for today, okay? Just changing standard form to trig form. I just did something with 2s. Let's change it. Let's make it. Let's just change the whole thing. Okay, so let's write 2 plus 3i in trig form. Most of the time you're going to get decimals. Okay, so if we get a decimal, we'll just round it if we need to. Okay. What are the 2 things that we need to figure out to be able to write this in trig form? R and theta. It doesn't matter which one you do first. Either one. Let's do R first. How do you find R? Yeah, we're doing Pythagorean theorem. And if you need your point to kind of visualize it, it's like right there. So that line that I just made bold, that's your radius. So what's going to be my formula to find the radius?
2 squared plus 3 squared.
2 squared plus 3 squared. It's just finding the absolute value. That's all you're doing. 2 squared plus 3 squared. All right. What's 2 squared? 4. 3 squared?
9.
And 4 plus 9 gives me?
13.
So 13. So r squared is 13, which means r is square root of 13. We'll just leave it like that. That's exact. Okay, so now in terms of what we know the value that we need to fill in right there. Okay, we've got the r. Now we got to find what?
Theta.
We got to find theta. Okay. First, figure out what quadrant you're in. Are we in quadrant 1, 2, 3, or 4? We're in quadrant 1. What's the formula to find theta if you are in quadrant 1?
Theta equals arctangent times y of x.
So the inverse tangent of All right, no multiplying there. We're not multiplying anything. We're plugging something into a function. Okay, it's different than multiplying. So inverse tangent of, what's our fraction? 3 over 2. 3 over 2. If the 3 or the 2 were negative, I would have used the negative, but they were in quadrant 1, so they're both positive. All right, so now make sure you're in degrees. So inverse tangent of 3 over 2. 56 point, we'll call it 3.1. 56.31. That's my theta. Now, take square root of 13, 56.31, and fill them into this formula right there, and stop. That's all we do. So r cosine theta plus I sine theta. Okay, so r. Okay, so that's what you're filling into. Okay, so there's r, square root 13, cosine 56.31 plus I sine 56.31. That's the final answer.
It doesn't want us to simplify.
No, because if you multiply this out, if you take the square root of 13 and distribute it to cosine 56.31, you're going to get 2. And if you take the square root of 13 and multiply it by the sine of 53.31, you're going to get 3. So you're going to be changing it back to what you started with.
All right.
You could do that, like if you wanted to double check it. Square root of 13 times cosine 56.31. Well, I didn't get exactly 2, but that's because it's not exactly 56.31.
Should have saved it in memory.
We could have saved it in the memory, yes.
What's the point, like, what's the purpose of getting to this formula?
It's just fun.
Okay.
I agree.
Yeah.
Yeah.
Here.
Mathematical busy work.
I'm going to show you what we do with it in a second. So I'm gonna try one more with it, and then I'll show you why we do that. Yeah. Well, this is why you do it, but I actually want to do one more of these before we do that. So it provides a fast way to multiply and divide. Right, but let's try one more. So let's call this example 4, and let's do -2. We use a lot of 2's. Let's do -4 plus 5. Okay, and the directions are the same as example 3. Find the trig form. Okay, so what's one of the things that we need to find?
The radius.
Okay, need the radius. What's going to be my formula to find the radius? Yep, and when you fill in Pythagorean theorem, what will you have? 16 plus -4 squared. And what did you say that was?
16 plus 25.
16 plus 25. And 16 plus 25 gives me?
41.
41. So what's my radius? Square root of 41. Okay. So there's my radius. Now I need my angle. In order to find my angle, I need to know my quadrant. You don't really need to graph it. Like you've gone left 4, up 5. You should be able to visualize where that would be.
It's quadrant 2.
That's quadrant 2. What's the formula to find your angle if you're in quadrant 2?
180 plus the arctangent of pi over x.
Yeah, 180 plus the inverse tangent, y over x. Let's write that down. 180 plus inverse tangent. What's y in this case?
5.
5. And what's x?
Negative 4.
-4. Use the negative. Okay, so 180 plus the inverse tangent. 5 divided by -4.
That's -1.
That's not -4. Okay, so that's 128.66. And that makes sense that the angle is that big because you are in quadrant 2. Quadrant 2 starts at 90 and it ends at 180. 128 is right in the middle. So theta, what did I say? 128? 66. Okay. Now, write your final answer, just like we did on the other side. So R cosine 128, cosine 128. That's your final answer. Question on that one? Okay. So now, besides just being fun, why do we do it? So it gives us a very quick way to multiply and divide. What I want to do first is go over the old way. We've done this before, okay, dividing complex numbers. We'll do it the old way, and then I'll show you how much faster the new way is. Okay, the old way uses standard form. 2 minus 3i, 5 plus I. No r cosine theta here. It's the old way. When you had to divide complex numbers the old way, we didn't actually do division. We did multiplication. Does anybody remember what we multiplied the top and the bottom by? Not the reciprocal. Yep.
Square root of -1.
No. That'll be important to remember that I is the square root of -1 in a little bit. But it has something to do with the bottom. And it begins with a C. What is it? No. Anyone remember? No, not cross multiply. That is important for law of sines though, so remember that for the test.
You multiply by 1, which is the same on the top and bottom.
You are going to multiply by something that's the same in the top and the bottom, and it has something to do with 5 plus I.
5 plus I over 5 plus I.
Not 5 plus I over 5 plus I.
5 minus I.
5 minus I over 5 minus I. Okay, so even the first step, we didn't remember how to do it, right? And that's because there's a lot going on when you do it this way. So you got to first remember that. That's called the conjugate. Right? Conjugate. So now, multiply the top and the bottom by the conjugate. Now, in the bottom, and the top, you FOIL it. What's 5 times 5?
25.
So 25. What's 5 times negative I?
-5i.
But then what's 5 times I?
5i.
So that's a negative 5i and a positive 5i.
Cancels out.
Those are gone. Positive I times negative I. Well, what's a positive times a negative?
Negative.
Negative.
1.
I times I.
-1.
Well, let's leave it just as I times I for now. But just tell me what I times I would be. Would be I squared. Now in the top, what's 2 times 5? 10. What's 2 times negative I? Negative 2i. What's 5 times negative 3i? Negative 15i. Now we got a negative times a negative, which is a positive. What's 3i times I? Positive 3i squared. And we're still going. Now we gotta simplify that. All right. So now, what's negative 2i minus 15i? Negative 17i. And what's I squared? Another thing we got to remember. I squared is -1. So what's -1 times +3?
-3.
So that's really a -3. Now do the bottom. 25 minus, what did we just say I squared was? So you get a -1 inside, you still have that negative in front. Okay, so we're getting there. What do we end up with in the bottom? 26. Now we can combine 10 minus 3 and get 7. And if you're going to write that in standard form, you need to split it. So it's 7 over 26 minus 17 over 26. So that's how you have to multiply, or that's how you have to divide complex numbers if you use standard form. There's a lot going on. Look at all the things we did. We had to conjugate, we had to FOIL the top, FOIL the bottom, change the I squareds to -1, combine like terms with the reals and the imaginaries, then split it into 2 fractions. A lot of steps. Now, let me write something in trig form and show you, it's not going to be equivalent to the problem we just did. I'm going to make up something different. But let me show you how quick I can do it. Okay. Let's take 6 cosine 40, I sine 40, and I want to divide by 2 cosine 10 plus I sine 10. What? Well, I haven't started yet. I just read the problem. Now I want to do the problem. All right? So I'm going to divide these 2 things. When I divide these 2 things, this is the final answer. 3 cosine 30, I sine 30. Done.
Oh, that makes a lot more sense.
What I just did right there took the place of having to do all that stuff. The problem with it is you have to understand trig form. If you don't know trig form, you can't do it this way. So what I'm trying to point out, it's a lot faster. 6 divided by 2 is 3. 40 minus 10 is 30. That's the final answer. Yep.
So is that the trig form of the problem above?
This is just a totally different problem I
Okay.
made up.
Okay.
No connection. I just wanted to show you the length of the process in standard form versus the length of the process in trig form.
Okay, so it's just if it's outside of the parentheses, it's division, and then inside of subtraction. Is that what it is, or is that based
Yeah,
on?
let me write that down right
Okay.
now. So the one I just showed you guys is the bottom.
Where do we get the Z's from? What does the Z stand for?
So the z's just represent 2 different complex numbers.
Okay.
When we do an actual problem, that's a number, 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 that's a number. Those are all numbers.
So those are all Z's?
Those are all what?
Z's?
So there'd be all numbers, like I had here. A 6, a 40, a 2, and a 10.
Okay.
So I'm going to call the first number, just call it Z1. Then I'm going to call the second one Z2. So I don't have to say R1 cosine theta 1 plus I sine theta 1 every time. If you want to multiply Z1 times Z2, again, Z1 is all that stuff, Z2 is all that stuff. To multiply these numbers together, you take the 2 radii and you multiply them. You take the 2 angles and you add them. That takes the place of having to do all the FOIL. Having to multiply the first, the outer, inner, the last. Change the I squared to -1. All that stuff is simplified to just multiplying 2 numbers and adding 2 numbers. Much quicker. Now the bottom one, this one I showed you. If you have 2 complex numbers, call them Z1 and Z2, and you want to divide Z1 by Z2, take the radius of the first one, take the radius of the second one, and divide them. Take the angle of the first one, take the angle of the second one, and subtract them. And that's where trig form is very Okay, to multiply and divide. So no more worrying about what I squared is and all the stuff we had to do. But if my problem wasn't in trig form, then this probably isn't a shortcut. Like if you wanted me to divide these two numbers right here and do it in trig form, it's probably going to take me longer to change that to trig form, change that to trig form, then do it in trig form. It's probably quicker to just do it the way we did.
Yeah, need to copy that.
So this is really only helpful if the problem is given to you in trig form.
Are we gonna have problems that are getting to trig form?
Yeah, we're gonna do one right now. Yep.
Okay, good.
Okay, so let's multiply and divide. Okay, so I'm going to make up two numbers. Okay, let's pick a radius for Z1. I'd like to have a number that's even. 20? Okay, that's it.
24.
All right, and then let's pick an angle.
17.
17, okay. And now for Z2, I'm going to pick, yeah, I'll do 10. Cosine, let's do 5. So we just made these numbers up. So I want to do two things. I want to multiply these together, and I want to divide them. That represents multiply. Okay. When I multiply them together, what do I do with this number and that number? Multiply them. So you got to remember that. Multiply them. What's 20 times 10?
200.
So the final answer is 200 cosine. And what do you do with the two angles? Add them. What's 17 plus 5? 22. That's the final answer. Okay? So no worrying about all the stuff we had to do the first time I showed you.
And it's much better.
Yeah, but the reason I showed you the first time is because I want you to see how much better this is than the other way. Now we want to divide them. What do we do with these two numbers when we want to divide them? Divide them. What's 20 divided by 10?
2.
2. Okay. And what do we do with our two angles?
Subtract them.
Subtract them. And what's 17 minus 5? Oh. So we basically reduced a division problem to something we can do in our head. Versus when you do it the other way, there's no way you're going to be doing all these steps in your head. It's a lot of steps. So trig form gives us a quick way to do 4 things. Multiply, divide, I just showed you. And the 2 things I'm going to show you tomorrow are raising to a power and taking a root. Those are opposites, powers and roots. Does everybody have that? We're good?
Yep.
Let me just double check that real quick.
Thank you, my good sir.
You've done a great job.
No, that's good. Okay, so that's the homework on page 450.
That's it.
We'll go over that tomorrow and then finish up
Oh, that's it. 135.
1 through 3. 5. Yeah.
The what? What did you say?
edge.